So with that, I would like to introduce our speaker today, Joel Gottlieb. Joel joined D-Wave in January 2016 as a senior pre-sales analyst after 20 years at AT&T and AT&T Research. He earned his PhD from the University of Wisconsin at Madison in condensed matter physics after graduating from the University of Michigan. At D-Wave, Joel's role includes bringing new users to the quantum computer. He's heavily involved in our training, and he also researches problems which show the power of the system. Joel loves learning new subjects and new technology and also enjoys talking music. So with that, I would like to turn it over to Joel to get started with our presentation today.
Thank you very much, Susan, as always. It's a snowy morning here where I am in Vancouver. Thanks to everyone for attending this. And yes, we're going to talk about embedding, which is a subject, if you're not familiar with it and you're a D-Wave user already, hopefully by the end of this talk, you'll know a lot more about it, and I'll point you in the direction of learning more. If you're just learning about the D-Wave system now, hopefully this will lead you on to look at some of the other D-Wave videos which are on the YouTube channel and the webinar videos as well as a series of getting started videos that are up there on YouTube. So without that, with that, let's move on. So our goal today is to talk about using the D-Wave quantum computer as it always is, and we want to solve a problem. And I thought that rather than just dive right into embedding, I give a little background on what types of problems can be solved with it, so that then we can talk about embedding a little more fully. And for those of you who already know all this, bear with me. I would hope there'd be a little bit that you would learn from it anyway, even if it's a little bit of review. So what kind of problems can we solve? And Susan and her team did some research to come up with a list of over 200 early applications that people have written using the D-Wave quantum computer thus far over the last 5 to 10 years or so. And you can see from this slide that there's quite a variety of subjects on here: internet ad placement, quantum chemistry, particle physics, cancer drugs, formation of terrorist networks. It's very exciting, and we're hoping that this continues going forward. We are always looking, as Susan mentioned, that's part of my role, always looking for people to start using the computer. At the end, I'll provide you a link for how to do that right away. Whether you're in a company or not, you can do that by yourself and get started. Anyway, so what are these sorts of problems, and how do we break them down? And the first thing to talk about is that problems to run on the D-Wave are formulated as either what is known as an Ising model or a QUBO model. And I'll briefly talk about both of those now. The Ising model is a physics introduced subject that has to do, it was originally introduced by a fellow named Ernst Ising, who worked during the 20th century and was a German physicist who did a lot of his work in the US, lived a very long time. But he originally solved this problem in one dimension, and then people followed on with it, and now it's an integral part of physics. And basically, you assume that everything is pairwise interactions between something you call spin, where there's basically a two-level system, and the atoms, or whatever they are, electrons, photons, whatever, they can either be up or down, and then they interact with each other. There are two terms in the energy. There's a linear term that takes the place of sort of a magnetic field that might be on them, or some force. We'll talk about that in a moment. And then the next term, that thing with the SI and the SJ, those are interactions of pairs, so that each can affect its neighbor. And in the Ising model, the spins are only +1 indicating up and -1 indicating down. And then the other way to do it is called QUBO, which stands for Quadratic Unconstrained Binary Optimization. It's a mouthful, but basically what happens here is that the highest power of variable, like in the Ising model that appears, is 2 for the quadratic pairwise terms. You don't constrain the variables explicitly. You let the problem find it. The values are 0 or 1, and you minimize or maximize an objective function. So both Ising model and QUBO are just analogous ways of looking at this. And depending on your interests and your background, one might be easier for you to start with, but all problems can be shown to be equivalent mathematically. So how do we develop it? How do we develop a model? And this is, again, some more review. You start with a problem in the real world that you want to solve, and then you write a minimization function that incorporates basically 2 things. There's an objective, which is some function that you want to minimize. And you're going to minimize it by changing the spins, basically trying to influence them to be up or down. You have some variables, we'll show that in a moment, that you set, and then the computer returns an answer, and you're hoping it's a minimum, and then you have some constraints that have to be followed. And the general form is Ising or QUBO. Something to minimize is an objective plus some number, gamma, which is called the Lagrange parameter, times constraints. And Lagrange parameter is a fudge factor. It's a number that we look for when we solve a problem. We have sort of an idea what the range is, and then you vary it. We won't go into that today. That's in some of the other webinar decks that are out there. And here's just a briefly summarized example problem. If you're a sports fan, this would be something interesting to write, although it gets very complicated in a hurry. We want to choose a sports team, and basically we would assign our binary variables to say, is each player on the team, maybe it'd be 1 or not, -1 or 0, depending whether we're Ising or QUBO. And the objective function would be, you would have some function that you would come up with that would tell you how much the player is helping or hurting the overall team score or energy. And then the quadratic terms would be, maybe 2 of them together help you, or maybe 2 of them together do not help you, in the case of when they don't get along. But an example might be a pitcher that works best when there's the same catcher there all the time, or a football quarterback who has a favorite receiver, things like that, or 2 that just don't get along. And the constraints are basically, there's going to be a certain number of players that you have that can fill particular roles, and you can't have too many quarterbacks on a team, or you don't. You can't have too many baseball catchers, for example, then the players in a particular position. And then you also have constraints on the number of players that you can have as a whole. Now, baseball is obviously would be a very complicated thing, but I would guess someday at some point we're hoping to get someone will start working on that, because it'd be a very interesting thing. And the baseball, just an aside, has gone into this whole statistical era where they try really hard to use numerical modeling to figure out what's going on. And the quantum computer actually someday will be a fit for that. So here's the programming model if you're in QUBO. And I just want to mention this briefly. There will be some programming examples later, but for the moment, just to introduce, you might remember back there a bunch of slides how that Ising model looked with those SIs and the SJs. This looks like it also. The programmer sets the little AIs there, and then the BIs are also set by the programmer. Then the program is sent to the quantum computer, and it samples from the possibilities of those spins, the Q's, which could be 0 or 1 if it's a QUBO, and then it comes back and hopefully gives you the lowest energy solution. And then from there, you interpret it depending on the problem and what the variables are and so on. And we're not going to go into that today. That's in some of the other webinars. Now, in order to understand what embedding is, we need to talk about basically that your problem is a graph. In other words, you can picture it that you have selected particular qubits, if you will, particular things that could be either up or down, spins, atoms, photons, whatever they are. And we can draw that out as a graph. And the near neighbor interactions, the pairs, kind of determine what the shape of that is on what your problem is expecting. And in the case of the D-Wave quantum processing unit, it offers, what the graph that it offers is called Chimera. Upcoming later this year will be Pegasus graphs. And let's just show what a Chimera graph looks like. There are particular interactions that are offered. And here we have shown the structure of the current D-Wave architecture quantum computer, the 2000Q machine that is currently publicly accessible. Notice that there are 16 rows across the top, 16 columns, and then 16 rows, so 256. And each unit cell, which is drawn here by the little green arrows, has 8 qubits in it. And largely this is due to the wiring that's possible on the chip. The ones that you can see there, like 0 and 7, for example, are connected by a coupler. There's some circuitry in there that makes that possible. And it makes it possible for the programmer to do that, to basically apply some term, either a positive or negative term, as I showed on that programming grid. Now, as I mentioned, what is upcoming later this year is going to be the Pegasus architecture, which significantly enhances the connectivity, targeting about 5640 qubits, and a little more complicated of a basic notion of a unit cell. And one thing to mention is that the Ocean tools, I'll briefly talk about Ocean coming up, but there's also some webinars that have given an introduction to it. The Ocean tools are already there for exploring the embeddings and the architecture of the Pegasus layout. And I'll show you a couple graphs of that coming up just for fun. We expect that later this year. So adding a little detail, this is just the couplers obviously are a factor of 6 or 7 there. One thing that does increase a lot is the degree. Notice on the bottom row there that in the Chimera it's 6, corresponding to up, down, left, right, and then ones in neighboring cells. In Pegasus, it goes up to 15. So we expect more problems will fit, and that's a lead into the next topic. What does it mean for a problem to fit? In other words, you've got some graph that you want to run on the quantum computer, and what has to happen for that graph to be able to run on the quantum computer? And to introduce this subject, I'm going to introduce first just sort of an abstract notion of it, which isn't a D-Wave thing. But suppose that my graph that I want to fit on is hexagonal. And this is, again, not a D-Wave example, but I just want to get your mind around it a little bit. Suppose that the architecture is hexagons, like I've shown there at the right, and I want to put a triangle on it. In other words, I want to model a triangle on a hexagon. How do I do that? So the picture there with the ones in the middle, notice how there are 3 ones there on the top part of the hexagon, and then 2 2s and a 3. And what I want to do there is somehow do the math so that the ones end up behaving like they're all one unit, and they're the top vertex, say, of the triangle. And then the 2s behave like 1, call it number 2 when they're bound in some way, and they behave like the left side of the left vertex. And then the number 3 is by itself and behaves as the right. And so in that way, it is said we have embedded a triangle onto a hexagon. And if you look at the bottom one there, it's another way to do it. That you've got the 1 is represented by 2 of the qubits on the hexagon, or the nodes. The 3 is represented by 2, and the 2 is also represented by 2. And that's just another way to do it. So it's not a unique thing to embed, but we do have to think about it. So now let's go on to D-Wave. Suppose that my simple little problem is a triangle. Can I embed, can I assign a single physical qubit to each variable in the triangle on this particular architecture that I have shown here? So let's think about this for a second, looking at this picture. Can I do this? For example, at the far left there, notice that sort of diamond thing. It looks like a 4 fits on there pretty good, right? A for loop where any one of them is connected to the others around the outside there. But I cannot do that by a triangle. In other words, there's no way to start with 1 and go to another and go to a third and come back in 1. Like, notice across the row in the middle there that they don't connect through the center there across that row. They only connect up and down like that, well, at the angle, I mean. So what is not possible is to put a 3-loop or a 5-loop or a 7-loop, it turns out, onto Chimera. And so because of this, we have to do a little bit of mathematical trickery. And this is why I showed you that thing about a triangle embedding on hexagon, because I want to motivate what we're going to do this. Here's an approach. If I take qubits 0 and 4 there, never mind, I'm not talking that much about the numbering, but this is in the first unit cell. 0 can reach 4, and then I do a little bit of mathematical trickery where I constrain somehow 1 and 5 to have the same value. And if I do that, if I make those 2 qubits act like 1 logical qubit, then 0 can reach the little barbell, and 4 can reach it, and 0 and 4 can reach each other, and I've got it. I've got what I wanted. I've got that closed loop. And so what we really need to do here is find some way to embed whatever graph you're looking for onto the lattice that's under it, the structure that's under there. So here's an example of a quick problem that we want to solve on here. And oh gosh, I've actually, I believe, made a mistake here with this. Yes, I have. I'm apologetic. What this graph is, I did not check my slides carefully enough. What I want there is not, well, let me start over and let me show you, let me say what this is. Suppose that Xavier is friends with Yolanda, and then Yolanda is enemies with Zeke. What I want, though, is that arrow there between Zeke and Wanda, forget Wanda for the moment, and connect Zeke back to Xavier. Can I write a solution to this? Can I find a solution to this problem so that X standing for Xavier and Y standing for Yolanda, they're friends, but then Y and Z are enemies, but then Z and X are back to friends again? In other words, so draw the arrow on the angle there instead. And is that possible? So let's try to put that problem onto the quantum computer. Now, and here it is. It's drawn better in this case, so hopefully you picked that up. Sorry about that error on that slide. The way we do this is we have a QUBO that we have written up for these logical qubits, and The same QUBO can be applied for all 2-qubit pairs if I want them to be the same, that is, and there's a different QUBO if I want them to be opposite. And in this case, X and Y have a friend relationship. So I have this mathematical function, X plus Y minus 2XY minus 1. If Y and Z, I want to be enemies, as I do, it's 2YZ minus Y minus Z. It looks similar, but a little different. It has opposite sign, and then there's the minus 1 is different. And Z and X minus 2ZX plus Z plus X minus 1. And I add them together, and there's my QUBO. Now, what we're going to do here, though, is change the math a little bit to add a relationship between 1 and 5 so that we're going to represent 1 and 5 by a joined pair, or a chain, as it is called. And I'm going to say here that the math on this one gets a little hairy, and I will show you in a few minutes. Generally, you do not have to do this. There is software that will take care of this step for you. But in this case, I want to run it through because I want to show you what happens mathematically. Q0 and Q4 have a straight up relationship with each other. And then Q4 and Q1 and Q5, notice that they're sort of bundled together in the notation. They basically have that relationship from the previous slide. But instead of writing 1 qubit here, I've written Q1 plus Q5 and a factor of 1/2 because I'm adding them together. Then I do the same thing in this barbell thing, Q1 and Q5 and Q0. Notice that it's half the joined one there, minus 2 of the other, like it is on the top line, and plus the individual ones, n minus 1. And then we have to add something very important here, that in order to try to get those 2 qubits, 1 and 5, to have the same value, I have to put a constraint on them, essentially another part of the QUBO, which is Q1 plus Q5. It's that same relationship, minus 2 Q1 Q5. But I don't know at the start how strong I need to make this. And so we use a constant which is called chain strength. And at the beginning, when I first start to run the problem, I don't have any way to know exactly what chain strength is going to work. But basically, it physically arises because I have decided to bind 2 qubits together. And part of what we'll see as we go forward is that you can bind many qubits together. You can have chains much bigger than 2, and the chain strength plays a role. So when I get down finally to the QUBO there at the bottom, I've got terms like 2, there's a linear term, there's a term with a constant C, that's that chain strength, and these other things, and a C there too, and then some other constants. And this slide here with the embedding rules is only here for reference. It's a nicely summarized thing that shows you if you wanted to write a computer program to do embedding, you'd have to do all of these steps. A logical qubit can be mapped to n physical qubits. As long as they're a connected set, call that a chain. For each physical qubit, for each physical coupler connecting 2 physical qubits in the same chain, include QUBO terms to cause them to align. That's that chain strength thing. And then the remaining 2 get hairy, but this is a nice summary of what you'd have to do. Well, as I mentioned, you don't have to do this, at least not at first blush. D-Wave has introduced in 2014 an embedding algorithm. The authors were Macready and Roy, and it's provided there for your reference. There is a paper out there. If you want to get it, just type those 3 names right into Google right now and you can get it. Well, that is after you're done listening to us. But you get the idea. The idea behind the embedding algorithm was, given the problem that's been provided, given the user's graph, the graph that the user wants, and you got to put it onto this Chimera architecture, let's do that for the user so they don't have to go through that messy process I just described. Okay, I'm going to talk just briefly mathematically and very, very surfacey about this algorithm. The goal in this I gleaned from working through that paper. I wanted to know a little bit more about what's in there. Find the graph H, which is the smaller graph, like say the triangle, as a graph minor, it's called, of graph G. And their goal was to do this for, as they say, sparse G, when the big graph is not too connected, and H in the hundreds of vertices. And obviously you might be thinking back to that baseball problem. Yeah, that's probably more than hundreds of vertices. Anyway, when H is fixed, there's a polynomial time algorithm for determining whether or not G contains H as a minor. But if G and H are both general, then the problem turns out to be very hard. But if H is smaller than G, there are probably a large number of minors. In other words, I mentioned that earlier with the triangle being embedded onto the hexagon. There are always a lot of ways to do it. And I will tell you towards the end of this talk that there's been a lot of work on this in the last 6 years, and expect that work to go on happily for a long time. It's always good when a problem, you know, a solution like this that these three people did ends up kicking off a whole area of research. That's very exciting to me. But let me just show you a little bit how the embedding works on an 8-clique, which is a thing where any one of the nodes, like say 5 there at the top, has a direct connection to all the others. Notice that that's a connected graph, fully connected. 5 can reach the others, 2 can do it. On the right there is how it looks when you put it onto the D-Wave processing QPU and you get an embedding back. And notice that in the dark blue, there's a chain of 2. There's lots of chains of 2. And I see a chain of 4 there, it looks like. The red there to the right. Let's also do another example of a 20-clique, where any one of the 20 can reach any other. Notice like 4 on the left yes, it does. It has links to all the others. And this is what it looks like when you embed it. And I've just always thought this is kind of cool, that this algorithm is smart enough to find all these chains. The chains are not terribly long in this case. Like, I don't know if you can see my mouse, but like, I think that's a 7 chain in the pink there. And the purple looks like maybe 5. Not too bad. Obviously, as the problems get bigger, it's going to use up more and more of the terrain of the Chimera lattice. So now let's talk about the D-Wave Ocean API and how embedding is performed and how you would actually do it. And if you're not familiar with Ocean, it is highly recommended to check it out. A beautifully thought out API introduced about 2 years ago in Python. We had been doing other languages, and the authors of this were thinking really far ahead. There's a lot of deep stuff in there that even being embedded in it, sorry for the pun there, being even embedded in it for a few years, I still find a lot of things where I haven't fully caught up to what the guys that wrote this were thinking, which is wonderful. It's very deep. Now, before I do this, I show you any code, I'm gonna show you some results of the friends and enemies problem, where I ran a small problem using something offered in Ocean called ExactSolver, which is not sending it to the quantum computer, but only doing it on a solver that finds all the solutions and then gives me the lowest energy. Now, obviously, I wouldn't want to do that if the problem was too big, because it would take too long to go through all the choices. But in this case, there was just three vertices, and I programmed the chain strength directly. I wrote a program going back to that slide where I'd introduced that little number C. And here's what happens. If the chain strength is 3, there's 6 solutions that look like, here's 2 of them on the right. One is across the top, they're the same, which is good, they're friends. Then they're enemies, 1 into the 0. But there is no way to actually have a friend relationship from the 0 on the bottom back to the 1. It turns out there's no way to do it. And so there's 6 solutions. And if I up the chain strength to 5, I get 6 lowest energy solutions. But look what happens if the chain strength isn't high enough. If it's 2, I get 7, which is interesting. But then if I make the chain strength 1, there's only 1 lowest energy solution, and this does not sound right. You know, in other words, I expect I get the same thing. And what is happening here is that, remember when I put that chain strength in there, I had bound 2 of the qubits to have the same value. And it turns out that if chain strength is too small, then the chain is going to break, and the chains will not, the qubits will not have the same value. And so chain strength is big enough, it's got to be big enough to ensure that the chain member qubits have the same value. And in a little while, I'll go over exactly some realm that you can check chain strength in to give you a start on it. Now, if we want to do embedding in Ocean, here is a small problem. And if you're just starting out in D-Wave, Ocean, and all that, I highly suggest running this because it's a really simple problem. If we look through the Python, it's got a couple of imports just to pick up the access to the QPU and something called Embedding Composite, which I'll talk about in a second. I set a chain strength and I set, hey, computer, run this 100 times and give me all the samples. And this is basically a very simple little problem. And basically what I do here is I set up the embedding composite, which is a thing that says, for the sampler you have provided, that's the D-Wave sampler in there, embed the problem for me and then run it. That's that sample QUBO statement there, where the Q, the matrix for the QUBO, goes in, and the chain strength goes in, the number of runs go in, and then I print the results. And the one way to do this, the one disadvantage to this is that embedding composite was really designed not to give you access to the embedding that was used. And you might do that if you just want the results and you might not want to see what you got back. But the next one possible that I want to cover is called LazyFixedEmbedding composite. Notice here in the code, a couple things have changed. Yeah, the chain strength is similar or a little different just for exploring. I call LazyFixedEmbedding composite on the sampler again. And in this case, though, notice this line with the arrow, print sampler.properties of embedding. And what that does is when it comes back from the quantum computer, it returns the embedding that was provided. So you can see exactly what you're getting. And so what we expect if we were to run this a lot of times is that we would expect that for this small problem, briefly here, if you look at this Q, I've got qubit 0 there and qubit 1, there's a coupler between them. And qubit 0 and 2, there's a coupler, and there's 1 and 2. Basically, all that happens is that I'm going to get back, what do we expect? We expect at least one chain, and it's up to the embedding program whether to assign qubit 0 to the chain, or that is logical qubit 0 to the chain, or 1 or 2. And so we might expect that it would change. Now, another thing that it does is that it moves the problem throughout the chip. And part of the reason it does that is that we would want to know over many runs of it, is there any region of the chip that is not performing the same as the others? We would hope that our problem doesn't show any behavior of that, but it's a good thing to do the statistics and just see. So LazyFixedEmbedding composite is one you could use if you want the embedding to come back for you, but it's been prepared for you. And another approach is called fixed embedding composite. And what happens here instead is that it's your responsibility to go get the embedding. And there is a tool inside of the Ocean API with a great name called miner. In other words, going out there and mining for an embedding. The way it is called is you import minor, which I didn't show, but then find embedding, and you give it, basically what you're giving it there is the matrix that you have, and that tells it which qubits you want and the couplers. But this thing here, the D-Wave sampler edge list, tells it for the embedding algorithm, here are the qubits that are involved on this chip. The embedding algorithm is more general, of course, and so it can run on any chip that I want to run. And so then we'd get our response back, and the response has got in it all the samples that came back and so forth. In this case, I've done the same thing. I've done a sample QUBO and so on. Why are they called composites? One reason is that you can call them one after another. And I encourage you to look at the Ocean API documentation, and you can see how composites can be called. They do very many things, and the team is constantly working on adding features to this API. And that's another thing for me that's been exciting. It's been solidifying beautifully. A lot of, when it first starts out, you're afraid that it's going to change every day. It's not anymore. It's been solidifying beautifully, and you can see how it's stabilizing into something really good. All right, so I want to mention something here. I'm going to now use the approach 3, but I don't show you the program, but I want to show you the results of a run. And what happens here is that notice that there are 6 solutions. Please look at, first of all, to read this, look at starting from the left. That's the answer. Qubit 0 got set to 0, qubit 1 to 1, qubit 2 to 0. It has an energy of 0. Notice that there are 6 rows that look like that. And it was found 114 times by the computer when I asked it for 1,000 runs. And there's something else here called the chain break fraction, which I'm going to talk about in a minute. But one quick thing we always want to think about. Are there the right number of solutions? Yeah, there are 6. And notice down at the bottom there that there's some starting that have higher energy that are not lowest energy. Okay, good. What should these numbers be? Well, if there's 6 equal solutions in energy and I ran 1,000, I expect it to be 1,000 by 6, or about 166. And I did pretty okay. A couple of them or more. If you run it each time, you're going to get a different set of these values because the quantum computer is fundamentally probabilistic. We don't expect the same thing every time. But basically, this is good, right? The chain strength is 5. I expected 6. Now let's go on and see what happens if I run it with chain strength 2. Notice that in this case, there are 7 solutions. And this time, it's pretty good. But there's something happened here called the chain break fraction, and it's not 0. And what is this thing telling me? It looks like it's got a value of 1/3. And what does that mean? Chain break fraction, it turns out, is a number that you can get back in the response object after you run a problem. And it's a quantity that is defined per sample. It's the fraction of chains in the sample that broke. And so for this friends and enemies problem, the X, Y, and Z thing, I had 3 chains. 2 of them are just 1 qubit. They don't count as really a chain, but they're chains. They're just chains of 1 solo qubit. And then the other is a chain of 2 qubits. And if there's a broken chain in the sample, I expect 1, of course, and there's 1 of 3, so hence I end up with a chain break fraction of 1/3. Now there's some really interesting stuff underneath here, which I don't have time to go over. If there is a broken chain, you can specify an algorithm that applies a fix to it. By majority vote is one of them. That's the default, but there's others. And after the fix, the embedding composite will display them in the statistics. So there's a lot of nice features here. And just going back to this for a second, my recommendation is when you get your first problem onto the QPU, we'll talk about this. You're going to set the chain strength at some value, and then you're going to play with it and run it at some other values and see if the results stabilize. Notice the difference between here and here. Chain strength 2 clearly isn't good enough. And I got to go up to 5, and then it's gone. And I might run 10, and I might run 20, just to see that I'm getting the same thing. All right, so let's continue. We're going to vary the chain strength, start with some reasonable value. I'll tell you what that is in a minute. Try doubling it, tripling it. Is there any sign of broken chains? And if so, can you get rid of them by increasing the parameter or removing them? You know, in other words, if you do increase the parameter, will they all go away? If you can't, then something else is going on. But this slide, of course, raises an interesting topic. How do I know what the initial chain strength really ought to be? Macready and Roy in their paper doesn't say anything more than a large number. And the main reason is they can't. It's problem dependent. It's going to depend on what else you set up. And a first good estimate is it the same order of magnitude as the rest of the terms in the Ising and the QUBO? In other words, that one I showed you just had numbers like 2 in it. If you were to try an initial chain strength of 1 or 2, perfectly reasonable. You'd have to go up. Recently, someone sent a note to one of our message boards, and their QUBO had numbers in it that were like 20. And they tried it initially with chain strength of 1, and it didn't work out very well. What was the first guess for that problem? 10, 20, something on the same order of magnitude. And there are people working very hard at coming up with limits for this, but it is problem dependent. Some of our documentation talks about upper limits as well, where you don't want to overset it, but I'm gonna just say a couple things here. Try it first at a chain strength that's on the order of it. Why do we do that? If we were to scale the problem, this will guarantee that it'll stay in the mix with the other parts of the problem. In other words, we want the quantum computer to see all the different variations of it. And what happened to that case where the numbers were all 20? It got scaled, and it got too weak if it was 1/20th relative to the others. Someday, I'm expecting some smart person or persons is going to write machine learning software to find the chain strength. There have been efforts to do this, haven't coalesced yet, but it would be cool to do that. Finally, just to sum up here, a couple things about the additional embedding work. As I said, there's been quite a bit of work that's happened that I found, and I just want to briefly mention these things. The first one by Kelly Boothby and Andrew King of D-Wave is another way to do what's called clique embedding when you're embedding that problem that I showed earlier, the 8 clique and the 20 clique, which is fast. There's been some papers. Timothy Goodrich, the third one, was a graduate student that was looking at embedding, and this turned into a couple papers out of Oak Ridge National Laboratory. The final 3 are more recent, and they're very interesting. I think these are all really cool attempts to come up with algorithms that do it a little better. And part of the reason what I was hoping from this talk is to get you started. If you're really interested, in embedding, or you think your problem isn't doing very well and you want to know more, you could work with us, or of course, you can ask us questions about it, or maybe take a look at these and see where this is all going. And I expect even in a year, there will be a lot more papers about this. You might also want to explore our Qubits conferences at qubits.com, Qubits. There's all the past talks, and I believe at least a couple of these were presented there. All right, so to sum up, we talked about what minor embedding is, how it fits into the D-Wave ecosystem, introduced Ocean's approach to it a little bit. There's more, but we got there. Looked at a couple examples, the chain break fraction, how you can use that to see whether your chain strength is good enough. And finally, a plug for LEAP. This is our free offer. Please click the link and sign up. You get 1 minute free of QPU time in your first month. And then if you give us your GitHub ID, you can have 1 month free, 1 minute free after that every month. And a minute doesn't sound like a lot, except that most of our problems actually run in milliseconds. So you can do pretty good work with a minute. And I encourage you to do that. And there's also a good community board there, and a lot is getting discussed. And for me, this has just been really exciting. I've only been in this space 4 years, and already it's just moving really fast. And email me if you've got questions, or we can do it on the bridge here. But thank you very much for your interest, and let's go to questions.
Well, thanks very much, Joel. Again, if you have some questions that you have not yet asked, you can put them into the Q&A box. We have some questions. We have many that were answered during the talk, but we have some that we're going to ask Joel live. So the first one is, if 2 qubits form a chain, are they entangled?
No. So entanglement is a very different thing. Entanglement has to do with the wave functions and getting them into a space where if you measure one, you immediately measure the other. It's automatically turns out you know what the other's value is. It's been shown that that can be done over thousands of miles inexplicably. No, it's a different thing. Entanglement is a very wild topic, and you might know that the Chinese even put a satellite up where they showed 2 qubits were maintaining their entanglement over that distance. But no, that's an unrelated phenomenon. One other thing to mention is that D-Wave has shown that there is entanglement going on in the relationships between qubits on the chip. But unlike the gate model quantum computers, which makes it a part of the model and the physics and so on, the quantum annealing, which we do, we didn't talk about that today, doesn't include entanglement as a parameter. You sort of see it as an after effect, but it's not part of it. So no.
Okay, next question. How do we calculate the chain strength variable?
You basically do not. You guess it to start, and then seek out that the behavior of the problem is staying the same. The first guess of it you could calculate as roughly in the order of magnitude of the terms that are in your QUBO or Ising model. So as I mentioned, if the terms are all 20, then we'd start out with 20. If the terms are on the order of 1, start out with 1 and go upward. At this time, there isn't an explicit calculation for it, and it is problem dependent. So I encourage trying this on when your first problem comes up. And I'll make one other comment. Sometimes people, when they start, they have a really big problem and they just run it. Start with just a few qubits at a time as a small little subset of your overall problem, and see if you can get a handle on how it's behaving at that point. And then later, start to turn it up where you don't know exactly what's happening.
Okay. Next question. What are the conditions in which applying QUBO on a QPU is more efficient than in a CPU or GPU implementation?
What are the conditions in which? I think that's still really a research question. I think that the world is still basically looking for problems where it's just clear that it's going to be more optimal on a quantum computer. I think some of the things that we've explored have been, to quote one of our colleagues here in D-Wave, if it embeds well, it's likely to run well on the quantum computer. So for example, if a graph is very dense, if there's a lot of connectivity, it might not embed very well. We don't expect it to do very well. Problems like traveling salesman where there's a tremendous number of solutions that don't differ very much in energy, it will probably not do very well if the terrain is flat. Whereas I didn't show the slide, but we like to picture the space as peaks and valleys. If the peaks are not very steep and the valleys aren't very deep, you don't expect it to do very well. But if you can get a problem where they are, we expect it to do better. But I think that is a wonderful question. And it's kind of an open question that I would encourage whoever asked that to ask it again in a year, ask it again in another year after that, because I think that's sort of the holy grail. Can we find problems that show distinct advantage for us with a quantum computer?
Okay, and kind of a follow-on to that, I'm interested in solving NP-hard problems. Are we there yet with D-Wave or quantum in general?
Yes, there are a lot of programs written already on NP-hard problems, and a good paper to look for, you can Google the name Andrew Lucas, L-U-C-A-S. I believe he's still in a postdoc position right now, but on a winter break about 5 or 6 years ago, I think 2013, Andrew Lucas, then at Harvard, took CARP's classic 21 NP-hard problems and wrote QUBOs for them all and published it. And in the subsequent time since, he's revisited a few. The paper has held up really well, and it's really fun to try to write programs for those and see if your results make sense. So knapsack or max cut, traveling salesman is in there, Hamiltonian cycle, things like that. My other point on that question is I would encourage the writer to start right away and do it. Even if we can't claim we've got some sort of, it's faster on this computer. If you start now at this point and start running it, start using it, you'll be in a position to start learning. Maybe even your own research will lead to figuring this out. So I definitely think you're in the right place with that question. It's these problems are fascinating, and there's lots of space. I would encourage anyone who's listening, the whole field needs your interest. If you're interested in these sorts of things, there's a lot of room and a lot of hard work to be done. Okay.
Someone wants you to repeat the point you made about the relationship between the chain strength and the number of variables.
I did not actually make a point on the chain strength versus number of variables. The point I was making was the strength of the chain strength versus the size of the terms in the equation. If we look at the QUBO that we have, or the Ising model, and the terms are a specific size or all around the same size, we start the chain strength at about that number. The number of variables is kind of a different thing. For much bigger problems, the chain strength, we might naively think that it might be higher, but that depends on how sparse the matrix is. So I would say, no, I'm not trying to make that point. I was more making a point of try to set a value of this chain strength as a start that's on the order of the other terms, see how it behaves.
Okay. Next question, with the D-Wave advantage, and advantage, by the way, is the name of our next generation system with the Pegasus architecture that Joel talked about before, will there be better resolution in the on-site bias and coupling values once they're scaled down? Sometimes increasing chain strength introduces a lack of resolution there.
Oh, that's a fantastic question. I don't know. I think that, so am I still, can you still see my deck here?
Yeah.
Yeah, this slide does not show it. And I think I need not to answer that. I do not know if the resolution, which 4 or 5 digits at this point fundamentally changes. I do not know.
Okay. We've only got time for one or two more, so here's another one for you. If the D-Wave qubits are not technically entangled, could we point to the concept of interference as the active ingredient here?
Well, they are. I'm kind of hedging on this question just because the word entanglement is so loaded. There is entanglement that goes on, you know, that we could observe it. And Trevor Lanting, Lanting, led a paper in 2014 where they showed that. When we present, we'll often mention superposition and interference and entanglement as effects that are, I guess so. I mean, I'm just a little hesitant because of there's sort of a loaded context for those words in physics. You know, like if I picture interference, I think of a wave pattern on a wall, you know, with white spots and dark spots and so on. It doesn't feel like the same thing. I'm not answering that very well.
Okay, well, here's the last question. The occurrences of global minimum solutions in the energy spectrum seem sometimes more than 3 sigma away from the expected frequencies. I think in the 2019 tutorial, there's an example showing this. Did anyone notice this or study more systematically?
No, I would love to. I would, if that individual hasn't contacted anyone else, I'd love to at least dig into that problem. No, I'm not aware of the discussion of it.
Okay. Well, I think with that, I see there are a couple more questions, so maybe our panelists can quickly get to those. But with that, we've come to the end of our time. So I'd like to thank you all very much for joining us today. We do these webinars on different topics monthly. So you can expect that will be one, I think the next one will probably be the end of February. We haven't yet announced it, but stay tuned. You can follow us on Facebook or Twitter or on our website, and we announce them. And also if you've signed up for LEAF and opted in to get notifications from us, we send out emails periodically with information about the upcoming webinars. So thanks again for your time. We hope you found this of value, and we hope to see you back at a future webinar. Bye-bye.